All right. Okay, it's a pleasure to have Ronen Eldan today. He'll be telling us about um, concentration bounds using stochastic calculus for Boolean functions. Ronen received his PhD from the Tel Aviv University, and he's been at Microsoft Research, and now he's currently at the Weizmann Institute of Science. And Ronen has really fantastic work on the Talagrand conjecture, on convex geometry, on KLS conjecture, and on on bandits in convex geometry, and a whole sequence of works on this. And today he'll tell us about his latest work on using stochastic calculus approaches for Boolean function analysis.
Thank you so much, Prasad, for this introduction and the invitation. I'm always super happy to be in Berkeley in this nice weather. There is an air conditioner here, so it actually doesn't matter so much where I am. All right, so let me start. So I guess the intro part will be easier in this series of talks because I guess most participants have already seen what a Boolean function is. So our setting is just going to be, we're going to have some function f from -1, 1 to the n to -1, 1. This is a Boolean function. And mu is going to be the uniform measure on the hypercube. Maybe let's fix the notation Cn to be -1, 1 to the n. Okay, and today, so this talk is gonna revolve around concentration inequalities. What are concentration inequalities? Those are basically inequalities that bound the global oscillation of a function by the local oscillation. So we want to say that if a function is not oscillating too much locally, then it's also not oscillating too much globally. And how do we measure oscillation? So the global oscillation will usually be measured via the variance of a function. So let's all agree that the expectation of f will just stand for the integral of f d mu. And the variance of f will just be the expectation of f squared minus the expectation of f squared. Since f is a Boolean function, this first term is always 1, right? Now, so that's our way to measure global oscillation. How do we measure the local oscillation? For this, the notion we like is the notion of discrete derivatives. We just want to see how big they are. So let's define the discrete derivative, the partial derivative of f in direction I at the point x to be just f of x1 up to xi minus 1, and then I force the ith coordinate to be 1, xi plus 1, etc. Minus the same thing where I now force the ith coordinate to be -1. And it's gonna be kind of convenient to normalize this by dividing by 2, doesn't matter so much. So this is the ith discrete derivative, and the discrete gradient at x is just going to be the vector of discrete derivatives. Good. And we're going to say that a function is not oscillating so much locally if its, partial derivatives at the point are small. A notion that we're also going to like is the ith influence of f, which is just going to be the expectation of the ith derivative of f squared. Of course, the derivative is either 0, 1, or -1, so the square here doesn't matter so much, but I'm leaving it because it's going to make sense for some of the inequalities which hold for functions which are also not Boolean, real valued. And the total influence, I of f, is just going to be the sum of the influences of coordinates. Okay, so I guess you've all seen those notations several times in this series of talks. And we're now ready to formulate the first canonical concentration inequality, which is the Poincare inequality. So this is the most basic way to relate local to global oscillation. It just tells us that the variance of f is bounded by the, I think the right constant is 1, I'm pretty sure, by the total influence of f. Okay, if the derivatives are small, the function does not vary too much. And this, it's not very hard to check that this is sharp. So for which functions this is sharp. In the Boolean case, it's only sharp for a dictator, but if f is real valued, it's not hard to see that it's sharp for linear functions, if and only if f is a linear function, actually. And when f takes the values -1, 1, f is linear if and only if f is a dictator. Meaning f of x is just xi for some I. Okay. Good. So this is the proof of this is very easy if you know of the Fourier decomposition. We'll see it a bit later. But now the next thing I want to do is I want to argue that this inequality is very lacking in the sense that it doesn't at all take advantage of the fact that f is Boolean. Okay, so it's actually true for any real valued f, and we're gonna see several ways of taking advantage of the fact that f is Boolean, in which will allow us to improve this inequality in several directions. Okay, so first of all, let's notice that it's far from sharp. So it's far from sharp for the case that f is the majority function. Okay, we kind of would have expected, if it's sharp for dictator and our world would be isotropic, then, majority is just some rotation of dictator. But this inequality doesn't work well with the direction 1, 1, 1, 1. It only works well with the direction 1, 0, 0, 0. So to see this, let's just quickly think what so the left-hand side for a majority is O of 1. The right-hand side for a majority, so what's the probability that we are near the boundary of f, that we're sensitive to one of the coordinates. It's not hard to see that this is something like 1 over root n. But if we're sensitive to one coordinate, then we're sensitive to something like O of n coordinates. So we have probability 1 over root n to be sensitive to n coordinates, which means the total influence is something like root n. So for majority, we get like O of 1 less or equal to, you know, omega of root n, which is far from sharp. Okay. So the question is there a way to fix this in the sense of, meaning, is there a better inequality which is sharp for maybe all threshold functions, hopefully all weighted majorities, or something like that? Okay, and the answer is yes. There is an inequality by Talleyrand saying the following thing. We first need, maybe let's make a definition. We define the local sensitivity of the function f at x to be the norm square of the gradient of f at x, which is just equal to the number of coordinates I, such that f at x is not equal to f at x with the ith coordinate toggled. And the Poincare inequality can be reformulated as follows. So we just have that the variance of f is at most the expectation of h of f. This is just another way to write the same inequality. And what Talleyrand proved around 94 is that we can add a square root inside the expectation here. So if you think about it for a minute, for majority, this is exactly, okay, up to a constant, actually. I'm not sure what the constant is. For majority, this is exactly sharp up to a constant, right? Because we have probability 1 over root n that the thingy inside the expectation will be root n. So both sides are like O of 1. Okay, this is the first strengthening of the Poincare inequality. And now I want to discuss another strengthening in a somewhat orthogonal direction called the Kkl inequality. So let's now recall what the Kkl and linear inequality is. So again, let's go back to Poincare and think of a function f that has variance O of 1. Think of, say, a balanced function. We have probability 1/2 to be equal to +1 and 1/2 to be equal to -1. And the question is, what can I say about the what can I say about the maximal influence of a coordinate? What does this ensure me somehow, the fact that the variance of f is O of 1, that there is at least one coordinate with a big influence? And how big is this influence? By the way, I see that there are questions in the chat from, like, I couldn't get a chance to read them, but if you guys want me to answer
so maybe you can answer Shah's question.
Sure. So let me look. Just let me know when there is a question, because I don't.
Just reading now, so you didn't miss it.
I see. So the Talleyrand result, there is a version. I mean, the version I wrote here doesn't make so much sense if the function is not Boolean, because we don't know what sensitivity would be. But yes, it does extend to non-Boolean functions, and the way to extend it is really to look at like this definition. We'll actually kind of, we'll kind of discuss this in a bit.
I think there is also someone that wants to ask a question. We allow him to talk. Okay, so Morph Martin, you want to ask a question? I'm not sure.
He's probably getting coffee.
Okay. So let's continue, and maybe we will say if there are questions in Q&A or in the chat.
Okay, so back to the discussion I started. So suppose I know that the variance is O of 1. Can this ensure that I have some influence which is not too small, and really how big can I ensure that one of the influences is? And you know, what follows trivially from Poincare is that there is at least one influence which is 1 over n, right? The sum of influences is 1, so one of the influences is 1 over n. And you know, this gives rise to the natural question, is there a construction of a function such that all of the influences are at most 1 over n, even though the variance is like omega of 1? Okay, or is it the case that, you know, maybe the structure, the fact that the function is Boolean, the discrete structure maybe enforces something better? Okay, and the Kkl inequality tells us, yeah, you actually do get something better. You get something better by a logarithmic factor. So the Kkl inequality looks like this. So it looks kind of like the Talagran inequality. But we also gain another term. We get to divide here by the log of E over the max influence of the function. And it's not very hard to see that this implies, for example, that if the variance of f is omega of 1, then, okay, so it implies this implication that there is a coordinate such that its influence is at least not 1 over n, but log n over n. Okay, and this improvement by log n at first it may not look like a big deal. It's only a logarithmic improvement, but actually it has very far-reaching consequences, which I'm not gonna discuss just because I don't have so much time, I guess. Good, so what we saw so far, just to put this on a diagram, we saw that there is this Poincare inequality, which is obviously it's implied by the Kkl inequality. It's not very hard to see that this is a strengthening. And well, then we had another inequality which it's also not hard to see that this implication is also true, but well, it's it's actually true under the extra assumption that the variance is omega of 1. So I'll discuss this a bit later, but maybe for now it's kind of okay to assume that all the functions we're looking at have variance omega of 1. And
Ronen, why isn't it true always? Like the influence is like the expectation of h of f.
yeah, this is bigger than 1 always. Yeah, you're right.
Okay, so for Boolean function, it's, I guess.
Yeah. For Boolean functions, it's, yeah, for Boolean functions, it's always, yeah, you're right. So forget it. Yeah, we're talking about Boolean functions, and then this implication is just correct.
But for non-Boolean,
for non-Boolean, there's a star here. Yeah.
Mm-hmm.
Right. So, and as we said, somehow these two things are kind of orthogonal to each other, and none of them is stronger than the other. So none of these two implications are correct. This, as we said, this is kind of tight for weighted majorities. This is pretty bad for weighted majorities. If you check this on majority, you'll see that it misses again by something like root n. Instead of root n, it'll miss out by root n over log n. So it's pretty bad, but this is sharp for something called tribes. Which roughly speaking is just take your coordinates, partition them into subsets of size roughly log n each. And then inside each of these subsets, you do an AND between all of the things, and you do an OR between the different tribes. It's not very hard to check that this is sharp, and tribes is kind of like, you know, it's an example where all the influences are the same, and they are all of this order log n over n. Good. So we have this thing, and to complete the diagram, it's kind of natural to ask, you know, is there some inequality that we can find that implies both of these? And this is what Talleyrand asked. By the way, I see there's quite a lag between my voice and the writing, right? Is it kind of okay? Because when I look at the other screen, I see that it's really lagging. So if it's annoying, let me know, and maybe we can try to.
Seems okay, I think.
Yeah. Okay. Cool. Okay. So this is the question that you know, this is a natural question that Talleyrand asked, and he even had a suggestion for what this strengthening might be. Okay. So what he proposed is the following inequality. The variance of f is hopefully bounded by this thing, but also hopefully we get to multiply by the following thing, 1 over log of 1 over the sum of the squares of the influences of f with the square roots. Okay. So this is what Talagon suggested. It's clear that, you know, this implication holds. And let me now also convince you that this implication holds as well. The other one. So
Ronen, in this inequality, the 1/, square root is not inside the expectation, right? That's something.
It's outside the yeah. I mean, it's just a constant.
It's
so
just a
you know,
constant.
this thing doesn't depend on x.
Right. And
So,
is there?
I mean,
is there any intuition why Talagrand suspected this form of the inequality?
Yeah.
Okay.
Okay. So first, let me show you why this actually implies Kkl.
Can I ask? I mean,
Sure.
It's a general question. I mean, maybe we can comment on it later. So, I mean, if you replace Boolean, I mean, if you try to relax it to being, let's say, almost Boolean or being bounded or being completely, you know, mapping to R, can you say at some point what forms stay true, what forms are obviously false? I mean, that's the question.
Maybe let me try to discuss this in the end. I mean, yeah, there's several things I can say, several other things I don't know, but I think it's gonna be better to try to discuss, because I mean, we'll also see from the proofs where we actually extract, you know, use the fact that it's Boolean. Okay. For example, Kkl really needs the fact that all the derivatives can be either 0, 1, or -1.
I mean, okay, if the function was very close to 1 or -1 on every point, so it wouldn't be true.
Sure. So it really just uses the fact that the derivatives are either 0 or something that's actually significantly bounded away from 0. This is basically what you need.
Okay, so you're saying, so if it's approximately Boolean, it's still okay?
Yes. Yeah. For example.
I'm not sure, because you can have two values that are very close to 1, then their difference would be very close to 0.
I mean, yeah. As long as those differences have to be the same order, you know, that contribute to the variance. Sure. I mean, if you have, you could have, you know, -1 and then 1 and 1 minus epsilon, but you only have like this one point where you have -1, and the whole game is between 1 and 1 minus epsilon, and then, as Avishai says, you can't really gain anything. It has to be the case that, you know, the contribution, that like most oscillation happens where, you know, the differences are quite large. Sure. Yeah, so this is, I guess, what I have to say for now. On the other hand, what's written here, it's like much less crucial that the function is Boolean. Okay, and for this inequality, we'll see what happens. But maybe it's a good time to comment that this kind of inequality, one of the first applications was to show something for first passage percolation. I'm not going to define what it is, but it's basically you have a percolation and it determines the length. It's like the length of the shortest path. And then this function is not Boolean, it takes integer values, but the derivatives are, you know, integer. You're muted, Shachar. If you were talking.
No, I'm talking to the kids here.
Okay.
Muted, yeah.
Okay. Good. So actually, okay, let me go back just a little bit. So this implication is not quite true. It's only true for functions such that the variance is omega of 1. but there's an actual strengthening of this conjecture. This is what we're gonna prove. So maybe let me now write what the strengthening is. It's almost the same as what's written here, but what you actually get to have is this: there exists a function g such that everything I wrote here holds, but you also get to put this function g inside the expectation here, and g of x is always between 0 and 1, and the expectation of the square of g is at most the variance of f. So I feel like I don't want to confuse you too much. I will just need this thing in order for this implication to hold true, but you know, you can just ignore the function g if you want, okay? Obviously, this is yet another strengthening just because, you know, g is between 0 and 1, so I only made, you know, this thing smaller. And now let's see how, let's call this inequality star, and let's see how star implies the Kkl inequality. This is pretty easy, but at least it'll give you some intuition on, you know, what this thing is good for, maybe. So here's how this implication works. So the inequality basically says that the variance of f, maybe let me write here, times root log 1 over the sum of squares of influences is at most the expectation of g root the sensitivity. I just copied the inequality, but now let's use Cauchy-Schwarz. And Cauchy-Schwarz tells us that this is at most the square root of the expectation of g squared times the square root of the expectation of the sensitivity. Now, the expectation of the sensitivity is just equal to the total influence of f. On the other hand, we have this inequality. So this is at most root variance f times total influence. And now I can divide by this, divide both sides by the square root of the variance of f. And what we're gonna have is that the variance of f is at most the sensitivity over log of 1 over the sum of squares of influences. And well, this sum is obviously smaller or equal, like I guess I'm talking about the denominator. So maybe let me just write it here. Is definitely smaller or equal than the max influence times the total influence, which means that, you know, this is smaller than the total influence log, and here I can write 1 over the total influence times 1 over the max influence. And this is almost KKL, right? If we could erase this thing, sorry, if we could erase, not including the log, if we could erase just this thing, we would have KKL exactly, right? But the point is, you know, it's not very hard to check that if this is the dominant term, right, this product becomes a sum of logs. And if the first one is the dominant term, it basically means that the influence of f is already very big. So KKL holds like trivially. So it's not hard to check that we can actually erase this thing. Okay, so this is why this implies KKL. Okay, and star is basically, so this star here is our first main theorem. And okay, maybe let me say one more thing. So just to give you an intuition regarding this sum of influences square, if you think about monotone functions, what this is just the energy on the first level of, like, the first level Fourier energy of f. Okay. So basically what this inequality means is either there's considerable energy on the first level, which means that f is very correlated with some linear function, or if it's not, which is equivalent by a theorem of Binyamini, Kalai, and Schramm to the fact that f is noise sensitive. So f is noise sensitive if and only if this thing here is little o of 1, in which case you actually get a strengthening of this original inequality here. Okay, so whenever f is noise sensitive, you get something which is strictly better than what's written here. Okay. Good. And before I continue, I mean, let's continue and discuss one last concentration inequality, again due to Talagrand, but a different one. So this one is, the previous one was Talagrand 94, and this one is Talagrand 96 or something like that. And this is a strengthening of the Kkl inequality. So the Kkl inequality told us, again, that the variance of f is at most, and let me write it a little bit differently. So the total influence is the sum of influences, and here in the denominator, we had log of 1 over the max influence. And what Talagrand proved is that we can actually remove this max. Right, so this is a very natural thing to expect. Basically, what this inequality is telling us is that, you know, the influence is really not the right quantity to measure the effective variance in a certain direction. When the function is Boolean, the effective variance is really this thing. Like, those are the things that add up to the entire variance. And if you look at the tribes function, then, you know, this inequality is sharp. I mean, I guess what I'm trying to say is that, you know, the contribution of a single coordinate to the overall variance of the function is this quantity here written inside the sum. Okay? And there was a question floating around of trying to characterize, so we know this is sharp for tribes, but we'd like to characterize, give some characterization of what does a function look like when this inequality is sharp, for which, what can I say about functions such that this inequality is sharp or sharp up to a constant for. And our second theorem basically says that if this inequality is sharp, then you have a lot of vertex boundary. So for this, let me just define that the vertex boundary of f is just all the set of x such that the gradient of f at x is non-zero. And our theorem is the following. So if I, let's give this right-hand side a name, let's call this T of f, and let's define our Lagrange of f to be the ratio between the variance of f and T of f. And, you know, the Lagrange inequality just tells us that this is at most 1 or at most some constant. I think you can actually take 1 here. Doesn't matter so much. And the theorem says that, maybe let me write it here. So the actual theorem says that if you take the variance of f and multiply it by this quantity over log 1 over r tal of f. So this is clearly at most 1 just because of this inequality. But what we show is that this is also lower bounded by the measure of the vertex boundary of f. So one consequence is that, you know, if this thing is actually 1 or omega of 1, not much smaller, then the vertex boundary is of the same order as that of the variance, which basically means that, you know, most points, you know, the variance is kind of like the expectation here. They're also of the same order because it's a Boolean function. So it means that most points where f is 1, or a proportion of points where f is 1, are also inside the vertex boundary. And a corollary of this is, again, some kind of stability bound for the so-called isoparametric inequality. So just to quickly remind you, the isoparametric inequality says that the variance of f is at most something like this. This is a sharp inequality. It's 2 times, sorry, let me write it like this. The total influence of f is at least 2 times the variance of f times log 1 over the variance of f This is log base 2. This thing is sharp for subcubes. And this is the isoparametric inequality. The corollary says that if I is sharp up to a constant, so if a function f almost saturates this inequality, then in this following weak sense, it's close to a subcube in the sense that the measure of the inner vertex boundary, this is a bit stronger than the vertex boundary of f, is at least some constant times the measure of the set where f is equal to 1. So a subcube has all the points inside the vertex boundary. If you almost saturate the isoparametric inequality, that you have a proportion of the points inside the vertex boundary. Okay, does it make sense? Good. So those are the theorems that we have. And in the time I have left, I want to talk to you a little bit about the approach.
Ronen, we have a question.
Yeah.
What is the definition of this derivative plus?
This is, okay, so this derivative was just vertex boundary. And by derivative plus, what I mean is the inner vertex boundary. So these are the sets where f is equal to 1, and also they're in the vertex boundary, which is kind of much stronger. It's a stronger statement, because if you take a very small subcube, say, then you have a lot more points in the vertex boundary than in the inner vertex boundary, right? If it's codimension k, then you have a ratio of k between the two. So this is just, I mean, the point that the fact that we can take this plus here basically means that we get something that is sharp up to a constant. Okay. So let's start with some constructions towards the approach. Just a few general words. So maybe if I go back to this diagram, I'm looking at the screen and it seems like there is a lot of lag. Okay, so the Poincare inequality here on top has a very simple proof using Fourier. This inequality, its first proof due to Talleyrand was some kind of induction on coordinates, whereas this inequality, the Kkl inequality, as well as the second inequality by Talleyrand, they're the main component somehow in those proofs is the hypercontractive inequality. Our approach somehow completely bypasses hypercontractivity. And just to give a teaser for what's going on is hypercontractivity basically tells you like that the philosophy is start from the original function, apply some noise to it, apply the heat operator, and then you get some function which is much smoother. And the hypercontractive inequality tells you how much smoother it is, And the fact that it's smooth lets you do several things to it. We kind of, instead of heat equation, take a dual approach. So heat equation can always be coupled with some diffusion process. The heat equation, you know, in Rn is the expectation of the function on some Brownian motion started from a point. And, you know, we can, instead of applying heat equation, we can apply some diffusion process. But in our proof, it's really the diffusion process that we use is really analogous to the reverse heat equation, in the sense that if heat equation takes a function, starts noising it, and eventually reaches something completely flat, reaches the constant function, in our setting, in our approach, we kind of start with a function where you have no information at all. We start from a constant thing, and we kind of go backwards in time rather than forward in time, eventually ending up at the original function where the whole analysis is looking at derivatives not as things become more and more smooth, but as we have more and more information about the function. So this was very, very general, and I know it sounds very vague, but I think, but just keep it in mind as we go through the proof, okay? Okay, so we need two general ingredients for proofs. The first one is one that I guess you're all familiar with, and this is the multilinear or the harmonic extension of a function from the discrete cube to its convex hull, the continuous hypercube. So what is this? So given a function defined on the discrete hypercube, I guess everybody here knows that it can be uniquely written as the sum over subsets of coordinates of some coefficients depending on those subsets times the characters, which are just the product of coordinates in these subsets. Okay, so, okay, I wanted to move this, but it doesn't work. And f hat, which is often called the Fourier transform of f, is, it exists and it's also unique. Okay, so this is a fact, just follows from the orthonormality of these characters. And this expression basically automatically induces an extension of f into the continuous hypercube, right? Just by, this thing makes sense as a function where those xi's are continuous, right? So this, and by abuse of notation from now on, when we write f, we'll you know, f can refer to both the function defined here or here. They coincide on the discrete hypercube, so it doesn't matter so much. And one thing to note is that this expression is multilinear, which means that this function is harmonic. And not only it's harmonic, it's also harmonic in the relative interior of every one of the k facets of the continuous cube. So another way to think about this definition, which might make more sense for what we're doing here, is to start from a function defined here on the corners, and then we can uniquely harmonically extend it into the one facets of the hypercube. Once we did that, we can extend it interpolate inside the two facets harmonically, and so on until we get to interpolate everything into the continuous cube. This would give the same result as, you know, what this expression is. Okay. So this is the harmonic extension, and the second ingredient is going to be some kind of random walk. I know I'm basically running out of time for the first hour, right? So let me just write a few more lines, and then
you can take the break in a natural point. I mean, it's not.
Yeah. Sure.
Exactly.
So just yeah, sure. So our second ingredient is going to be a process BT. So a stochastic process, T is going to be between 0 and 1, and BT is going to live inside the continuous cube. And this process will be characterized. So I'm not going to give you the explicit construction now. This I will do after the break. I'll just tell you there is a unique process which is characterized by the following properties. It's a pretty simple process. So the first property is that, well, the process is essentially one-dimensional in the sense that all coordinates are IID. So I just need to tell you how one coordinate behaves. The second property is that for all I and all t, b t, the ith coordinate of b of t, is in absolute value almost surely equal to t. Meaning that bti is either plus t or minus t. And the third property, which is going to be enough to give us a unique characterization of what this is that bi of t is a martingale. Okay, so I guess this is a good time for a break, because now in the break you can try to think how to construct a process that satisfies, you know, both 2 and 3.
So these properties uniquely define the process, or
almost. I mean, I'm cheating a tiny bit by saying the time is continuous, so the martingales can be either left or right semi-continuous up to this tiny point.
Mm-hmm.
It's unique.
Okay, sounds great. So let's take a 10-minute break. When we come back, if you have questions, it will be maybe a good time to ask them. And see you after the break.